This lecture will serve as an introduction to atomic orbitals. In order to best make sense of this, you should have a relatively good understanding of both the particle wave duality of light and of electrons. So I'm going to start off with Schrödinger's equation. Yeah, the same guy with the cat. And this equation right here. Now, if you ever go on and discover a class called quantum mechanics and get really involved in that, you will learn how to solve this equation. We're not going to do that in this class. It is beyond the scope. However, I want to talk about it because the plots that we use to describe orbitals are a solution to this equation. So what orbitals really are probability distribution maps. So in other words, here is a region and an electron is going to exist somewhere in this region. That's what it is. And we use this equation to describe that. So we have this Hamiltonian operator, which is the total energy. It's the potential and kinetic energy. The wave function, which describes the wave-like nature of the electron, and then the actual energy of the electron. And so if you solve this equation, psi, right here, this wave function, if you square that and put it on a graph, that is what an orbital is. Okay, so it's not important that you be able to use this equation at all. What is important is that you understand that these orbitals, they arise from a mathematical model. And that's kind of where we're going to leave that in general chemistry. Okay, so we are going to focus on the plots of these orbitals, and so I want to describe them. And so we use something called quantum numbers to describe electron locations. And there are 4 quantum numbers, and I'm going to go through those, and then we're going to briefly apply this concept. Okay, so the first is the principal quantum number. That is n. That describes the size of the orbital. So first off, you have to know where you're at in space. How large is the space? Then we have this angular momentum quantum number. It's script L. It describes the shape of the orbital. And then there's the magnetic quantum number, which describes the orientation of the orbital, and then the spin quantum number, and this is related only to the electron. It's basically the orientation of the electron. So I'm going to go through these 4 and kind of describe what they are, and then we'll get to practice applying this. So the principal quantum number determines the overall size and energy. Okay, so you've probably seen a diagram similar to this in the past. This is the Bohr model of the atom. So you have your nucleus, and you have increasing energy and increasing size. So the possible values for these orbitals, or for these principal quantum numbers, is a positive integer starting with 1, and it could technically go up to infinity. There's not really a limit. And this right here, this is a hydrogen atom, and this is what the energy would be at this n equals 1 level in hydrogen. Okay, so that Schrodinger equation that we talked about, you can solve that, and it will be different for all the different atoms. We are only going to focus on the hydrogen atom here, because it's much easier to deal with because it's just a single positive charge surrounded by a single negative charge. So if you're wondering where these numbers come from, that's where, and you don't have to worry about it, and you don't have to memorize any of these. So the energy of this energy level, it's negative 2.18 times 10 to the negative 18th joules, and it's multiplied by 1 over n squared. So if it's n equals 1, then this would just be 1. So the n equals 1 is just negative 2.18 times 10 to the minus 18th joules. And then you'll notice that as you increase in energy, the levels get closer and closer together. Okay, so you just kind of want to pay attention to that, understand this, and this isn't to say that the orbitals themselves necessarily get closer in space. This is a plot of energy. Again, this is a model. This is a mathematical model for understanding what is happening to an electron that is in that region in space. Okay, so the angular momentum quantum number, that's the L. This determines the shape of the orbital. And this value of L will always depend on the value of n. Any integer from 0 up to n minus 1. So if n is 1, then L has to be 0. If n is 2, then L can either be 0 or 1. If n is 3, then L can be 0, 1, or 2. And we'll practice applying this later, but for now I want to talk a little bit about how we designate these and how we write them. So n is always a number, 1 through infinity, and then in order to avoid confusion when writing these out, we use letters to describe this one here. And so the value of L corresponds to a letter designation. And so if it's 0, then our letter is S, and we call that's a sphere. The value of L is 1, it's a P, and it looks like this, and this is just a mnemonic here. You can come up with your own, but it's a peanut. 2 is the D orbitals, and they look like this kind of, and that they say double peanut. I don't know. I feel like that's a cop-out. I could probably come up with something better, but I'm not really sure what I would call it. But you might be able to come up with something different for this. That makes sense to you. And then value of L is 3. We call that the F orbital, and that kind of looks like a flower. It's multiple. It's like a bunch of these all stuck together in different orientations. We call this a flower. So you would then keep going up E, D, F, G, H, etc. But we won't go beyond that in this class. We're not really going to entertain what that would even look like. So this is really the max values that we're going to see in here. So when we write these out, we would write the number for the S orbital followed by the letter for the L orbital. So 3s would mean an electron has a principal quantum number of 3 and angular momentum quantum number of 0. The magnetic quantum number specifies the orientation of the orbital, and it depends on the value of L. So it's any integer from negative L to positive L. And we're going to talk about this in more detail in a minute because the orientation gives you an idea of which axis the lobes of the orbital lie on, basically. So it'll make a lot more sense when we go through the pictures in just a minute. The spin quantum number. So this specifies the orientation of magnetic spin of the electron. There's two possibilities. There's positive half and negative half. Okay, so the electron can spin up or spin down. And we're not really going to go into detail about what spin is. It's actually a really complicated concept, but when we talk about where the electrons live or the address of the electron, this spin will become really important for designating where they go. And we'll talk more about that in our next unit. But it's only ever going to be plus half, minus half. Those are your two options. You can think about it as spinning clockwise versus counterclockwise, but it's not actually spinning on an axis. It's not like a top, but it's really, it's not super important to understand the spin. Again, you just need to know this here. Okay, so I want to apply this briefly here. So the atomic orbitals are always defined by the first 3 quantum numbers. The shell, you may have heard of electron shell, that's defined by our n. So n equals 1 is in the first shell. This would be the second shell, the third shell, and that's our principal level. And then the subshell is defined by L. So you have the subshell of 0, or the subshell 0 or 1, or the subshell 0, 1, or 2. And then you'll notice that the number of subshells is equal to the same as the principal quantum number. So the principal quantum number n equals 1, there's only one subshell. If it's 2, there's 2 subshells. If it's 3, there's 3 subshells, and so on. Okay, so I want to go through these pictures really quickly. You don't need to worry about exactly where this all comes from, but I just kind of wanted to show what they look like. So again, this is that sphere. This is the s orbital. It looks like a sphere. And it's just a large circle. Then you have your p orbitals. And so you'll see how you've got p -1, 0, and 1. So what that is the p is our L, and this number right here is our m sub L. So this would be, these orbitals would have a n equal to, well, we'll just say the n is 2. Our L is 1, it's p, and then our m sub L would be -1. And then you'll see for d orbitals, it starts at -2 and goes up to 2, +2. And then with our f orbitals, the principal quantum number has to at least be 4 in order to have a angular momentum quantum number equal to 3, which would be the f. And then we have a -3 up to 3. And so these, again, these are graphical representations of the wave function from the Schrodinger equation. We're not worrying about solving it. I just really want to make sure that everyone is clear that these came from a mathematical model. So we tend to draw atoms as spherical. So if you think about the overlap of all of these orbitals, it's going to look like a sphere. And I'm going to show you a little video illustration of this. So here you have a 1s orbital. Okay, so we're going to look up here, you can kind of see the 1s, 2s, 3s overlap. So then the 2s, it's another sphere and it kind of encompasses the 1s orbital. And then you have your 2p. So 2px, that would be like saying 2p sub 1, 0, and -1. It's just instead of using a number here, they're using a letter because the axes are labeled. It's not super important right now. We'll talk about that later. But you can see how they kind of start to look like a sphere. Okay, you've got the 2s, and then you've got these p orbitals. And so it looks like, mostly looks like a circle. And then each of these areas, these are all places that an electron can exist, where an electron can be. That's what they are. So that sphere defines the boundary around which an electron is zooming around. These lobes here define an area and where the electron can also zoom around. Okay, so we talked about these orbitals. So what is the consequence of having orbitals like that? Why do we even envision an atom like that if it's not really what's going on? Well, there's this little feature of an atom that if you hit it with some energy, you'll see something happen. So if you take a piece of metal and you put it in a flame, you'll see a color. If you apply a current to gas in this tube, you'll see a distinct color. And these are 3 different elements, and you're seeing 3 different colors. What's happening is the electrons are jumping from the ground state to the excited state, and then when they fall back down, they emit light. And the distance that they fall, this wavelength, right, corresponds to color that we see. So if the wavelength of this light emitted by this transition falls within the visible spectrum, we will see a color like we do here or here. If it doesn't, then we won't necessarily see color. We might feel heat, IR, or have some other consequence of electromagnetic radiation, but we wouldn't see it because it's not visible light in that little spectrum. So what's happening is electrons are able to jump between these states. And so this model of the atom as having discrete energy levels is what we use when we're trying to explain this behavior. So atomic spectroscopy is a really cool technique that we can use to learn about the world. So you have an electron in the ground state, and you zap it with some energy, and it absorbs a photon. So it absorbs a packet of light energy. That's what our photons are. And it moves. So we have this electron here, and it moves. So now it's in an excited state, and then when it falls back down, it emits light. And so that wavelength of light corresponds to the energy. So we have our energy of that photon equal to hc divided by lambda. So in other words, it's equal to Planck's constant multiplied by the speed of light divided by wavelength. Okay, so if you know the energy, you can solve for the wavelength. Now, this is a specific atom, a specific element, and when hit with energy, the visible wavelengths that are released when they fall down correspond to these colors. And they are discrete lines. It's not a spectrum like white light. These are discrete lines. And so thinking of the atom as having these discrete energy levels is what allows us to interpret this spectroscopy graph. Okay, so if jumping from here to here has energy that corresponds to blue, then we'll see that color. And then the electron cannot land in between levels. It has to go between these actual levels. It has to land right on them, like stairs. It can't exist in the middle. So these transitions, these energy transitions are kind of set for different atoms, for different elements. And so you get these, what we call them like fingerprints of different elements. So here is the emission spectrum for hydrogen. We see a violet here, blue, green, and red. And they're of these specific wavelengths, and we can measure this with instruments in the lab. And when an electron starts on the n equals 2, principal quantum number of 2, so it starts at the 2 shell. If it excites to the 3 and then falls back down to the 2, that's red light. If it's excited to the 4 and falls back down to the 2, blue-green light is emitted. And if it's excited to the 5 and then falls back down to the 2, then that emits violet light. And so here we have a graph of sorts showing that if you have n equals 1 and you have transitions to the n equals 1 level, that's ultraviolet wavelengths that are emitted. The visible wavelengths start with electrons at the n equals 2 level, and they get excited and fall back down. And then IR is up here. So you'll notice that if you're at the n equals 1 level, those transitions have more energy than the transitions at the n equals 2 versus the n equals 3. Okay, so ultraviolet light has a shorter wavelength, a higher frequency, and higher energy, compared to IR light, which has a longer wavelength, a smaller frequency, and less energy. So white light is all wavelengths of light, And atoms have these discontinuous colors. They have bright lines at specific wavelengths. So this here is helium. And we can actually use this information to identify elements in space. So each element has its own unique emission spectrum. You'll notice that, look at neons, right? It's all those colors. So if you've ever seen a tube of gas, neon gas shot through with a current, a neon light, it's an orange color because these are the colors that neon emits when those electrons jump from the n=2 level and then they're excited, and then they fall back down and emit light in this region. So a gas tube filled with neon gas will look like red, orangey, yellow colors. So what we can do is we can actually look at something like a star, like our sun, and we can see what elements are in there because we can look at the emission spectrum. So just to clear up some vocabulary, you have an electron absorbing energy. It's excited. This is unstable. So the light is emitted as the electron falls back down to the lower energy level. So this is excitation and emission. If we want to find the change in energy, we always take the energy of the final and subtract the energy of the initial. So we always take where the electron ends. So if we're looking at excitation, this would be the final. And if we're looking at emission, this would be the final here. And again, we're only talking about hydrogen, so it's that negative 2.18 times 10 to the minus 18th. And then it's multiplied by 1 over n squared of the final level minus 1 over n squared of the initial level. So again, if we're looking at just the energy of the level itself, there's no subtraction, it's just 1 over n squared. But if we're looking at the difference in energy, we can use this equation to solve that. Now, there's a negative sign here because the electron's losing energy. So make sure that you keep your signs as they are because that's really, really important. It tells you if your electron either gained energy through excitation or lost energy through emission.